Welcome, everyone, to another ConsenSys Cypherpunk Hackathon workshop. Today, we have Gautam going over prove knowledge of a secret using gnark, if I'm saying that right. Gary Gnome, gnark. The zkSNARK, that's right. So just a quick housekeeping around Crowdcast. This is the platform we're using today. On the right-hand side, we have the chat area, which you can, of course, have conversation there. We'll keep an eye on that. I'll keep an eye on that. While he's going through the workshop. Hello, Youssef. And then we would love for you to ask questions to Gautam today, and please load those into the Ask a Question queue at the bottom there. It will be an easier way for us to know that you have a question, and then when that happens, we can also allow you to come on stage and ask the question yourself if you'd like to interact. Sometimes that's a great way to kind of have more of a conversation around your question. If you start to type the question, you put a question mark in the chat area, and then you wait to hit return, you'll notice a little orange button that pops up, and then you can also add it to the queue that way. So a couple ways to do it. The other thing that's the benefit of adding to the queue is that I can also record that specific answer to that question so that later you can replay you can kind of go through and see where those questions were answered. Of course, speaking of that, this is available for replay almost immediately after the broadcast at the exact same link. All the workshops are, as a matter of fact, to make it nice and convenient. We also will share Gautam's slide deck so that you can check that out afterwards if you missed anything or if there's any links in there that you'd like to access. Of course, please join us on the ConsenSys Hackathon 2021 channel. That's where we'll repost all the replays, all the links, all the good stuff from these workshops, as well as you can still RSVP for upcoming workshops. I know we're getting close to the end of the month, but we do have a few more. And of course, we'd love for you to sign up for the actual hackathon, which is June 7th through 11th. And there's a sign-up form at the shiny green link there. It's on our Confluence page. If you have an idea and a team, or if you need a team for your idea, or if you just want to jump on a team to hack out an idea during that week, we can help get that sorted for you. And also, minimum requirement for our teams, just because it was short notice and we know a lot of people are tough on time, is 2 people. So really, you can have a team, 2 people, and you're really good to go. And there's some great prizes to win. So I'm Shay, and without further ado, I'll hand the mic over to Gautam.
All right, thanks for the intro. So quick intro of myself. I've been with ConsenSys now, I think, almost 4 years. The last 2 years, I've been working on the gnark project, which is a zkSNARK library. And I'm particularly interested in how to use zkSNARK on Ethereum to improve scalability and privacy. So the goal of this talk is to kind of take a bit more time than the previous talk we did to explicit why zkSNARK are very interesting for blockchain and Ethereum in particular, and then to see how to concretely use a library that we develop, which is gnark, to implement circuits and to verify that on-chain in a Solidity smart contract. So the first part is kind of going to go into an overview of why zkSNARK are interesting and what's so unique about this construction. Then we are going to understand a bit all the terminology that's used around zkSNARK proofs, like circuits and prover algorithm and these kind of things. And finally, we have a slide just to not make lies the title of the presentation and to see how to actually use that on-chain. All right, so I'd like to express this as a problem that, as was presented in other workshop, I think it was the Ethereum 2 workshop, what we want to do is the blockchain to be secure, decentralized, permissionless, and censorship resistant and whatnot. And we want to transact on that, but we are really not happy about the transaction throughput. So we want to do more than 5 or 10 transactions per second. And also, it's probably not a very good idea to broadcast all the private data on a public network. So there are the 2 main problems that's been pushing blockchain research, I would say, the past few years. And really, if you look at the protocol level, so at the layer 1, simplification of the scheme, whether it's proof of work or proof of stake, the transactions are aggregated by miners into blocks, which are then propagated to the network. And one of the things is all the network nodes will then re-execute the block to compute the state. And doing so, they convince themselves that the block is valid and they update the state. So the strategy here to to put that in other words, is to ensure the computational integrity of the state transition function. All the actors or many actors on the network is going to execute the exact same computation. And obviously it has some issues because it's slow and you have to wait for the last one, and also because you want to execute the computation, you have some privacy issue because you need to have all the inputs available to actually run the computation. So let's see what zkSNARK can do about that. Big picture, again, just to put in other words what I just said, blockchain do computational integrity in a sense, and they are going to execute an ordered set of transactions. And before and by before I mean before zkSNARK kind of solutions, we re-execute everything. And after, the idea is you gain some advantages and two properties. One is scalability, where you are going to be able to execute some transaction only one time. And instead of having all the nodes in the network re-execute the transaction, have them verify a short proof that is going to guarantee them with overwhelming probability that the result is correct. And the second property is that we're interested in, and it comes from the zk part of zkSNARK, which is called zero knowledge, is that this proof can actually hide part of the inputs, and that's a much stronger property than conventional encryption, where you encrypt the input, but the inputs still go encrypted on the network. Here, the inputs don't even go on the network. They are completely omitted from the network, and that's what makes them very unique on that respect. So to talk about what are zkSNARK under the hood, I'm going to make a small detour, and sorry if there are cryptographers in the audience. This is very high level, don't hate me. I'm going to make a lot of imprecision and approximation onto that. So if you consider digital signatures that are used everywhere in blockchain, right? Particularly the one based on elliptical cryptography here for my illustration purposes. The idea at a high level is Alice has a public and a private key, and she can sign a message M with a private key. And then Bob can run an algorithm that's called verify signature that's going to take the message and the public key and the signature, and it's going to say, yes, this is a valid signature, or no, this is not a valid signature. And the whole signature scheme in between the proving and the verifying of the signature is basically just a specific mathematical statement. And the statement says somehow, here is my proof of knowledge that I know the discrete logarithm of a point. So again, not going to go into too much detail, but just to say that the signature that you see everywhere is a proof of knowledge, but it doesn't match the description of the zkSNARK per se. And I will go into more detail into that on the following slide. So now why I introduce that through that is that with zkSNARKs, you can actually encode any and many of these mathematical statements into circuits. And by that, instead of Alice just proving that she knows the discrete log of point, she can also prove that she knows the input of a hash function, or that she knows the solution to an equation, or any kind of mathematical statement that you want. Typically in cryptography and blockchain, we're interested in things like she can prove that she verified the signature off-chain and verify it on-chain, or she can prove that a Merkle proof is valid. And what's even more interesting is you can actually combine all of this into a single proof and into a single circuit. So it's much more general than signatures in a sense, and it has also interesting properties on successiveness, and I will go to that on blockchain stuff. So the example I want to use here to finish this introduction is, let's assume that you want to prove that the Ethereum transaction went correctly. And by Ethereum transaction, I mean that Alice wants to send, say, 10 Ether to Bob. And to do that, typically on the network, you'd have to check that Ethereum node would have to check that the balance of Alice is enough and do this transaction, but she also has to, the network node also has to check that the transaction is properly formatted and that the signature is the one of Alice and she actually owns the account and so on and so forth. And if we wanted to do that in a SNARK, what we would do ultimately, and what we will see on the blockchain, is Alice sent to Bob the state of the blockchain before, the state after a transaction, and she sends this proof that's basically this 3 elliptic curve points. So you pick 3 points on the curve to Bob, and Bob is going to use this point to convince himself that the transaction is valid. And admittedly, this is a very high-level view of the thing, but what's mind-blowing about that is, if Alice decides not to send only one, but 1,000 ETH transfer to prove the execution of not only one, but 1,000 different ETH transfer, the proof size and the verification size is the same. So the proof is only still these 3 elliptic curve points, and that's all that Bob needs to convince himself, almost all that he needs to convince himself that the transactions are valid. And that's the succinct part of the zkSNARK acronym. So the first S in zkSNARK is succinct. And that's a very powerful compression technique because you can basically do a lot of computation off-chain. And the way to verify that on-chain is always going to be short and small and neat. And that's the basis of something that most of you probably heard about, which are zk rollups, where basically you will have an operator operating nodes outside of the layer 1, outside of the main Ethereum blockchain. He can aggregate a lot of transactions, and then instead of posting all these transactions and all the states relating to that on the mainnet, he's just going to publish a proof on a smart contract on the mainnet saying, I did in fact process this transaction. Here is the state before, is the state after this, more or less. You have some details and variation of rollups on all this. But all right, so that was kind of, I think, for me, one of the most mind-blowing point about zkSNARK is this succinctness part, which make it very useful as a blockchain tool and very interesting for our purposes. The zk part is also very interesting, as I mentioned, the zero knowledge, where you kind of can hide some inputs, and I will go through that a bit later on this talk.
And Gautam, before you continue, just real quick. So if you have any links in your slide deck or anything for what you're going through, is it possible for you to post those into the chat just for people as it comes up? I don't know if you have any. Just wanted to remind you just so that they can follow along. Okay, thank you.
I have some at the end, but I will need to unshare my screen for that. But at the end, I will share them.
Okay, sounds good.
All right, so under the hood, what do we need to understand to actually kind of know what we are talking about when we say we are going to implement a zkSNARK circuit or do a zkSNARK proof? So I'm not going to go into how the mathematical scheme works, but we have some slides on that. If you are curious, we are happy in the question session to actually the guys in my team, Youssef and Thomas, are much better suited than me to answer this on the applied crypto part. But on the high level aspect of things, the main idea that you have to keep in mind is you are going to write a program, which is your mathematical statement as I mentioned it a few slides earlier. For example, in your program, you can say, hey, let's verify that my transaction is valid, that my hash is valid, that my Merkle proof is valid, or that an equation is valid, or that the balance from Alice account to Bob account is matching some rules. And this program is encoded into a graph. And the graph is what you see here on the right side of the slide, where each of the operations are going to be gates, and each of the inputs are going to be nodes. And the idea behind this type of representation is you are actually going to be able to assign numbers to each of the edges of the graph. And at the end, when you have all your graph with all your computation that's expressed, you can actually start to reason with the value of each edges that are constrained by the value of their parent edges. So you can actually write some equations, you can write some matrices representation of that, you can write some polynomials and some numbers. And really, most of the zkSNARK constructs that came out the last 3-4 years, and there's plenty of them, it's all about you have this type of circuit representation, which is a graph, you have numbers everywhere, you build some polynomials, and you want to prove that you know the polynomial, a polynomial here. And you have different ways of doing this knowledge proof of I know a polynomial, and that's kind of the variation that goes into the zkSNARK proof. All right, the next step at a high level, again, to understand what's happening, there are 3 main algorithms to use zkSNARK proofs, for most of them, again, the ones that we have at least. So here I introduced 2 names of proving system. As you can see on the right, there is Groth16 and Planck, and I'm just going to give a brief intro on that. So Groth16 is the zkSNARK scheme that's used in Zcash blockchain. And that's the one actually that's probably the most popular on Ethereum to use a precompile to verify proofs. And it has very interesting properties. The proof is small, the verifying time is small, but it has an issue, which is this first algorithm that I'm going to mention, the setup, needs to be done very carefully if you don't want to break the scheme. And one of the schemes that builds on that but improves this issue with the setup is called Planck, and it's developed by Aztec, and I'm going to go a bit more into detail on that if you have more questions a bit later. But anyway, the first algorithm you have your program, you wrote your statement that you want to prove, you have an algorithm that you have to run on this program that's called a setup, and that's going to create a key pair of proving and verifying key. You can see that as pre-computation, so it's going to use the structure of the program to pre-compute some values that will ensure that the proving and verification are cryptographically sound when you want to run them. So the second algorithm that you are usually going to run off-chain, which is the most compute intensive, is a proving time. So you are going to submit to a proof algorithm your program, your input X, which is private, your input Y, which is public. And I'm going to go into more concrete example of that soon, don't worry, just again to give the terms. And the proving key is going to put an object that we mentioned already that has 3 elliptic curve points in it, which is called a proof. And what will happen on-chain, again, usually in a normal blockchain workflow, is the verify algorithm, where, as explicited here, it takes a program, a public input, the proof, and the verifying key, and is similarly to a signature, is going to say this is valid or this is not valid. And just to give an estimate order of what takes so long, so the setup is run only one time, and it takes a lot of time to run, but you don't care so much because you run it one time. The proving time depends on the number of constraints, so the size of your program that you are going to want to prove, and is the most compute-intensive task here. It takes a lot of CPU and a lot of memory, but for example, for a Zcash transaction, which is something that is going to do a private transaction on a blockchain network, it takes about 1 or 2 seconds on a modern laptop to generate the proof. So it's not that crazy. It's practical, right, for many use cases. For rollups, you can actually batch many transactions, and even if it takes 20 minutes to compute a big proof because you wanted to batch proof 50,000 transactions, it doesn't matter so much because you are going to put this 50,000 transactions on one single proof on the network. And the verify algorithm in terms of performances and runtime footprint is very fast. It's constant time. Well, it's almost constant time. It's logarithmic with the size of the input, but it doesn't matter. Let's say it's constant time. It's basically running a pairing which takes about 5 to 6 milliseconds on a normal laptop. All right, so to sum up all this, first step, you translate your program to an arithmetic form, which is maths, and you don't see that when you use gnark, it's behind the scenes, but you still need to understand that you are not in a normal language, you have a specific mathematical representation of a program. Then you will run a proof algorithm that's going to compute a proof, and then you will verify that proof on a verifier. Good. So the two interesting properties at a high level, there is dozens of them on the crypto level, but at a high level that we're interested in. The first one is computational integrity. And the key part here is to verify the execution of a program. It's much smaller than to actually execute the program itself. So typically for rollups, where verifying 10,000 transactions that are valid and putting them in a block could take you a few minutes of CPU time, it will take only 6 milliseconds to verify that on the blockchain. The second one is the zk part. And when you check the previous slide, you have this notion of public and secret inputs. And you can not, when the verifier don't actually need the private input to verify the proof. Everything is done by the scheme, so you don't need to submit your private input. And one high-level metaphor that's often used to do that is, if you guys know about probably most of you know about the Where is Waldo book or game, where you have this book with a lot of characters and you have to find this guy Waldo with the stripes of white and red. And you want to prove to your friends that you know where is Waldo on the page, but you don't want to give him the solution because else he can just say, okay, I know it too. So what you do, you tell him to turn his head, you take a big sheet of paper that's bigger than the book, you pinch a hole in it and you put it on the head of Waldo, and then you ask your friend to look, and he can see that you know where is Waldo, but you didn't disclose the position of Waldo. So you kept some information for you, and it's kind of similar at a very low level of how zkSNARK can work. All right, so that was all the terms that I think are very important to know when you start getting started, I would say, to develop zkSNARK circuits. This notion of prover, verifier, proofs, and programs that are compiled into an arithmetic representation. So the past 2 years, we developed a library in ConsenSys called gnark. It's written in Go. Actually, I have a slide on that. It's going to be easier. So it's written in Go. It's very fast. It's faster than what's out there in the state of the art, I think, for Gross 16, and we're getting there for Planck, which is the other proving scheme that I mentioned, developed by Aztec. Compared to other zk library out there, we didn't introduce a specific language, we think that in between Solidity and whatever language you use for your backend and JavaScript and whatnot, you have enough language compilers and tools and ways to manage your package and dependencies that we don't need to introduce one there yet. We may reevaluate that in the future for more programmability, but for now we are pretty happy where we are at. One of the big advantages to actually just use Go as a language is you can do things like unit testing or benchmarking or doing package management and all this kind of with circuits without having to implement all that and maintain all that and multiple versions and whatnot. And moreover, you can also, when you integrate gnark circuit into your solutions, it's kind of easy to add some logging or some monitoring or to plug that behind the gRPC or HTTP API. You don't need to have a lot of plumbing to connect to processes that run like in other libraries. And again, the goal is to have a very simple API, so you can easily call this tree function setup, prove, and verify on your circuit. All right, so this slide I'm not going to spend too much time because it's more about the architecture of gnark, and as a user, you don't really care that much. It's just to give a broad overview of what are the components and what's really going on behind the scenes. So gnark is built on one big layer called gnark crypto, which essentially gives the crypto and mathematical primitives used by the upper layer to develop circuits. The upper layer has two main components. One, which is called the front end, and it has nothing to do with the front end in web development. It is borrowed from the compiler lingo, where front end is actually going to translate a program written in a language or with an API into a different representation. So that's the role of the front end. You write your program in some language, and we translate that into some mathematical representation. And then you have the backend, which is going to eat this mathematical representation and enable you to do setups, proof generation, and verification, and so on. I have some links here, but again, I don't have access to the chat, but we have a nice user doc. You can access it on docs.nark.consensys.net. And we have the GitHub repo, and I'm going to post that later on the chat. Or if you, Seth, maybe if you're in the audience, you want to post them, please feel free to do so. All right, so I think it's time to do some code. 20 minutes talk, good. Seeing what a circuit would look like. So I'm going to use an example that's used by, I think, in Vitalik blog posts and that's been taken in many other projects as an illustration. The idea is I have this equation here on the top left of the slide, which is x cub plus x plus 5 equals 35. And I want to prove to you that I know a solution to this equation, so that this equation is valid. And the idea with gnark is all you have to do is implement an interface, which has this defined function. So whether you're familiar with Go or not, it doesn't really matter. You have to implement this function on your object. And then to express your mathematical operation or your crypto operation, you're just going to use high-level APIs, where you're going to do, for example, cs.mul of your variables, and you can put as many variables as you want here, and it's going to compute your result. And for you, it's almost like writing with an imperative language, where you write your different equations or instruction, and you can add some assertions which are going to actually be asserted by the proof system. And one thing to note here, if you're interested a bit of how it works behind the scene, is what we are actually building with the front end when you compile a circuit is called a constraint system. So it's a list of constraints, a bit like languages like Prolog or this kind of stuff, where it's actually not an imperative language where you will say that this instruction is executed before this one and before this one and so on and so forth. You just have a list of constraints, and you are going to give inputs to the constraint, and the solver, which is going to help generate the proof, must say that all the constraints are satisfied or some of them are not satisfied, in which case you cannot create a valid proof. So it's a bit different than imperative programming. It's more declarative programming, and it's kind of, yeah, it's good to keep that in mind. So here on the left, you have what a graph would look like, as I mentioned on the first slide of this section, where you will you can see graphically this representation of the circuit where you have x, and here there is an x missing, but first you do x times x, then you use this result, so x squared times x, to compute x cub, which will be here. And then you add that, and you add that to constant that is 5, and you check that the result is 35. Last thing about the slide that I need to mention is when you declare your circuit, and so you can name it however you like, The key objects that you need to declare in it are called frontend.variables. That's where you declare them to be public or secret, where you don't need to declare anything. And so gnark supports, like, you can declare arrays or slices. What the compile function will do is it will actually use reflection to check the list of variables in your structures that are exported. So in Go, they are the ones starting with a capital letter, and it's going to instantiate variables with that. So all this thing, if you used other libraries like libsnark or Bellman used in zcash, that you have this nomenclature about assigning, instantiating, all this is done behind the scenes for you in our library. All right, so what does the code look like for these simple circuits? So first you declare it, you declare your circuit. So here it's actually, it's the same circuit. So you declare a circuit. You will first compile it with the front-end package, as I mentioned. You specify the elliptic curve that you're going to use, because we support different elliptic curves. We support BN254, which is the one supported today on Ethereum mainnet, but we also support Ethereum BLS 12381, which is going to be on Ethereum 2 and in Zcash, for example. And we support a couple of other curves that have interesting properties. For example, they enable some recursion in proofs, but we can get to that in the question if you have more details. We support 2 backend for now, so 2 proof systems. Again, if you have more questions, I can go a bit more into what are the differences. And when you run a compile on your circuit, it will output you this intermediate representation. Then you can use in Go, like in your test files, we have a wrapper that enables you to test your circuits. So you don't have any specific stuff to do, like you do it like other testing framework. You just create the input that you want to give to your circuit, which is called a witness. And you can use some assertion to ensure that the prover succeed with these inputs or the prover fail with these inputs. It's fairly straightforward to test that or to benchmark that into Go test files. And finally, if you want to put that in a main file where you want to integrate that into solution, you have, as I promised, this 3 simple algorithm where the setup is going to output a proving key and verifying key. The proving is going to output proof and verify that. Last but not least, so gnark supports exporting the verifying key into Solidity contract to verify your proof on Ethereum blockchain. So it only supports that for ECC BN254 curve. And the reason for that is that's the only precompile that's supported for pairing verification on Ethereum today. And idea is you're just going to pass a IO writer here, which can be a file or buffer, whatever you want here when you have your verifying key. And it's going to output you a standalone Solidity file with all the code needed to call the precompile with the correct inputs for your contract. And I'm going to walk through an example a bit later on that. All right, so I promise I'm not going to go into the formulas of that. I just wanted to demystify a bit what's happening behind the backend. For example, the zkSNARKs that most people know as zkSNARK, which is the one used in Zcash. These 2 algorithms that we're talking about, the prover and the verifier, they are not actually so crazy moon math or so complicated to implement. The prover is basically 250 lines of code, and the verifier is less than 100 lines of code. The prover is going to do a bunch of multi-exponentiation and some FFTs. And the verifier, which is what happened in Solidity, is going to do this pairing check here and a small multi-exponentiation too. But again, it's just a detail. Just to say that the verifying part is actually quite small and just has this pairing check, which is implemented through precompiling in the mainnet. And I think the last slide I have about how to write circuits and getting started is this kind of disclaimer on what you can actually prove in circuits, because it's each time you see a presentation or read a blog post about that, it always starts with this mathematical function or hashed things or very simple things, and sometimes it can be hard to do gymnastics and say, hey, I have my business logic and I want to prove something much more complicated into my SNARK. How do I do it? And the key part is, if you remember the graph representations that I showed you of program, each edge of the graph is a number, but these numbers are not numbers like ints or floats. They are called field elements, which are basically big numbers modulo prime. And you cannot do anything manipulating these numbers. Not only cannot you cannot do float arithmetic very easily or int arithmetic so easily, you have to worry, for example, about field overflow and these kind of things. So you really have to understand that when you write a SNARK circuit, your key citizen is not ints, is not float, is field elements. And some things like, for example, doing conditional, like if-else statement like you are used to do. Basically, when you are using a declarative language, what you are going to do in your circuit is you are going to say, if my predicate is true, I want this constraint to be satisfied. If my predicate is false, I want this constraint to be satisfied. And concretely, in the arithmetic representation, what happens behind this is each constraint is going to be instantiated twice. So when you do an if-else statement, you actually multiply the number of constraints by 2. And you can do it. It's just good to know that when you do it, it's not really efficient to do that. So it's better to have that in mind. There are some stuff also that are challenges that we're working on and other projects are working on, like doing virtual machine, like the EVM is a virtual machine, and doing that into a SNARK, for example, to prove Ethereum-like transaction. You have a lot of constructs that are not very natural to do in zk zero-knowledge proofs. Bit manipulation, field arithmetic that is not in the base field, and again, many details. I can go that into a question session. What works very well is when you do things that were designed to work with field elements. And so some specific hash functions, for example, SHA-256 is not designed to work on field element, not zkSNARK. MIMC is one hash function designed to work on field elements, and that's why it works well in SNARKs, and you see that. Similarly, signature verification, you have some specific signature verification algorithm like EDDA says it works in SNARKs, and others that don't. And again, the idea is not that you cannot do the others, it's just that the number of constraints and the size of your program and arithmetic representation is going to be so big that it's not going to be very efficient to actually do, for example, SHA-256 in a SNARK circuit. It is going to be hundreds, if not thousands of times slower than do specific hash function for that circuit. And now that's again, there are things like Plonk and custom gates and things like this is going to improve on that. But yeah, just again, something to keep in mind. And yeah, to conclude on that, where is the community at right now on that is, I would say the Graal for most projects is to come up with this thing called zk rollup, where what you want to do is you want to write your Solidity smart contract, say, or in a certain language, and you want your rollup to actually proofs that your contract is valid. So you are going to create a proof when you execute your contract, and the rollup operator, instead of just executing the contract for you, is actually going to batch proof into another proof. And to do these kind of things, you need to be able to do much more programmability at the zkSNARK level, and that's one of the challenges that we're working on. And the other part is you need to be able, in a SNARK circuit, to verify other SNARKs, which is called recursive SNARKs. And that's quite powerful. And if you're interested into that, we can give you some pointers to projects like Mina, for example, which has a whole blockchain, which is basically the idea. Each block contains a zero-knowledge proof that verifies the zero-knowledge proof of the previous block, and so on and so forth. And so the final block only has basically one zero-knowledge proof saying, oh, the blockchain is valid. All right. Last slide. Hope you don't have PowerPoint fatigue. Just to say that the title of the talk is not a lie. So there is this kind of exercise. I noticed that most of the workshop didn't actually go through a hands-on session, so I'm not going to put you guys through that, but I'm going to go through what exactly do you need to do to prove a secret using gnark, and I actually have a repo, a GitHub repo, open source with a solution on that, but just going to right to the point. So to prove a secret on a blockchain, what you can do is you can pick a secret off-chain, right? And you can create a hash of the secret. So we are going to use MIMC as this hash function, as I mentioned, because it's much more efficient to do in a zkSNARK circuit. So you do that off-chain. So off-chain, you have your secret and your hash. And what you're going to publish on-chain is just the hash of the secret. So nobody can learn anything from the hash of the secret. Nobody can deduce your secret. Once you have that, your circuit is just going to assert that you know how to compute a hash of a private input, which is called secret, such that the result equals a hash that is public. And the workflow is, I mentioned, the first thing you're going to do is you're going to run setup that are going to generate key pair proving verifying key. Then you export this verifying key to a Solidity smart contract, and then you compute and verify the proof. So from there, I think raise hand. So I can just quickly give you a walk through the solution, then we can have some time for Q&A. Let me see, can I click on that? Amazing. Oh yeah, and just before going to that, again, please check the link of the doc. We have a doc that that has a lot of examples and go through some concepts that I just mentioned into a bit more detail about what are zkSNARK, what are the properties, and so on. It's very interesting. So the workshop thing. So I have a small tool. Okay, let me first start by going to the circuit. I think this is the most interesting part. So as I mentioned, your circuit, you are going to define your variables. The one that is public is called hash, and we notify that it's public through this struct tags in Go, saying it's a public variable. And the second one is a secret, so you don't mention it. The definition of the circuit is very, very simple. We have a component into gnark that is going to call the hash function for you. So basically, you just say, I want to assert that the result of my MIMC hash call on my secret equals to the hash result that I provided. And that's it. That's all you need to do. And what the verifying key in Solidity looks like is this large Solidity file. The first one is a pairing library, which is standard one. We didn't implement it, right? We have the correct copyright here on who did that. And it's basically just a wrapper on the precompile to call the pairing API in the elliptic curve on Ethereum. So if you assume that we're going to need to call that. The contract that is generated by gnark is called the verifier, and it has a bunch of information here which are derived from the verifying key. Don't need to go into the details, they are just elliptic curve points that we need to go and pairing points. Then it has this function called verify proof, where you are going to provide your proof. So your proof A, B, and C here are the elliptic curve point for the proof, and the input is your hash that you need to provide. And I'm going to show you how that looks like in Go. I think I have the, oh yeah, it's in the main. It's in the main file. So I used, because I didn't want for potential demo to have too many moving pieces, I just used something that some of you probably know about. It's called, okay, it's a simulated backend from Geth. So it's a fake blockchain, but that does everything with the execution engine. What it does is create a simulated backend, a fake blockchain. It deploys the verifier, so the Solidity smart contract on the blockchain, and that's it. So there is no too much fancy part happening on blockchain. And the main flow, if you see it on the repository, let me get back to the beginning. First, we deploy the Solidity. Then we read our circuit and our proving keys and verifying keys. So fairly straightforward stuff. We pick our secret. We hash it off-chain, right? Everything here is happening in your backend or in your Go program off-chain. Then you are going to create your proof. So the first step is you have this witness where you assign your public input, which is the hash, and your secret input, which is the secret that we just picked here. You create the proof with the Grow16 API. You verify it just to be sure that the proof is valid, right? It's not mandatory to do that. It's happening off-chain. And then the most annoying part, I would say, about the Solidity call is to be able to serialize your proof in the right format. And for that, I added a bit of documentation here to explain what Solidity expects as smart contract input. But basically, the proof serialization is standard almost between all libraries and Solidity and what we have. So the order of the point in the proof is the same. So you just need to serialize the proof with our API, and then you will pick each coordinate of each point to the proof to set the inputs of the Solidity smart contract. And that's how you transmit the proof to the Solidity smart contract. Now, if you do that in another language like JavaScript or Rust or Java, you have to do that with different APIs, obviously, and it depends how you call your Solidity contract. And that's it. So you can run this end-to-end test to verify that the contract indeed verifies the proof. And if you give a wrong hash, it's not going to verify this. So, okay, I think it's a good time to go on the Q&A and take a break. After that. Am I still online? Yes. Does anybody have any question that they want to talk about SNARKs or proving schemes or gnark or roll-up related questions, scalability, privacy? Well, I will take that for a no, I guess. All right, so I will assume that this marks the end of this workshop, unless Shai or well, don't hesitate to reach out to us on Slack if you have offline questions or want to know a bit more about how to concretely use that in the hackathon or in any application. You can ping me directly on Slack or any member of the team. All right, I don't know. Oh, awesome. All right, so I'm going to drop on the call. I think Shai or Tamar can keep up with that. Thank you everyone for attending. Bye.